the light from distant stars or galaxies has a distinct spectral features of the atoms in the gases around the stars. So if the galaxies are moving away from us, the absorption line, if you're a light source and then it comes through a little cold gas, then you will have, and those gas will absorb these things. And so you will get these absorption lines, or you have emission lines. So it's okay. So I think I'm going to go with that. So basically you have these lines, and these are like your fingerprint. So for example, your helium, you have hydrogen, you have unique lines. So unique shapes, it is like your fingerprint, right? Very distinct to yourself, right? It's the same. So that's why scientists can see, oh, the sun has helium and whatever percent, and this whatever percent. They can estimate those elements by just looking at these absorption emission lines. Now, if the galaxies are moving away from us, these absorption lines will be shifted. So on the bottom, you see this absorption line when you see from the laboratory. Now, you have the stars and nearby galaxies, you go up, right, from the bottom. Then you have distant galaxy, you have very distant galaxy. You see these lines shifted toward red. We call this redshift. In this way, scientists can say that, oh, these galaxies are moving away from us, okay? So let me see, do I have to, let me just briefly go over. So the measured redshifts are usually stated in terms of a z parameter, z. The redshift z is the ratio of the change in wavelengths, the wavelengths with the source at rest. When z is large, we need to consider, large means z is like more than one, and then we have to consider the cosmological redshift, which I'm not gonna go into detail. It's the second one in the second row in this table. And in this equation, A now represent the size of the current universe, and A then is the size of the universe in the past according to the z parameter, which you don't need to understand here, okay? Which is fine. Now, let's solve this quiz, and if you solve this quiz, then you will understand what that is. So here, suppose light with a wavelength of 400 nanometer leaves a galaxy, and by the time it reaches us, its wavelength has been redshifted to 800 nanometers. So you see this equation in yellow. You use this. So lambda observed is 800, and lambda rest is 400. So what is z? What is the z parameter for this galaxy? Put your answer on the chat. First question: what is the z parameter for this galaxy? Should be very easy. This is not a difficult question. Just use this equation on top of the table, and you put 800 minus 400 divided by 400. Right, it is 1. Z is 1. Now, Z is 1, and in this table, select Z is 1. Okay, that is 1, 2, 3, 4, fifth row. You have Z is 1. Now, second question: how long has the light traveled to reach us? How long has the light traveled to reach us? So it is 7.731 billion years. And then because universe is expanding, the distance to the object now has to be larger than this in number. Okay, so that is on the third column. That's a 10.147 billion light years away. That point is now from us 10.147 billion light years. It's huge, humongous number. Okay, so that is how you go about with this redshift. Okay, so that's how the scientists can figure out this. I'm just giving you just an example for you to sort of understand. Okay, now, for example, the z parameter of a galaxy 20 million light years away is about 0.00154. See, so z is 1, z is 10. That is a crazy, number. In 1929, Edwin Hubble found a roughly linear relationship between the distances of the galaxies and their radial velocities. This means that the greater the distance between any two galaxies, the greater their relative speed of separation. So if you interpret this observation at its face value, What can you say about it? So you are looking at all these galaxies, and all these galaxies are moving away from you in any direction. What does that mean? If you just literally interpret the observation, what does that mean? Anyone? Put it on the chat. Any thought? What do you think? The universe is expanding. Yes and no, but if you look at literally, right? See, universe doesn't need to expand. You say just assume the universe is static, and you see this redshift. That means that these galaxies are literally moving away from us. Galaxies are moving away. That moves. Okay. So that is a literal interpretation. If you take that interpretation, what happens here is this means that we are at the center of the universe. If you take that and like actually. The Hubble himself, in his later days, he admitted that we might be at the center of the universe. Okay. But as Esther put, that's what I just said is not how scientists view the universe. So. 1922, Alexander Friedman derived this equation by simplifying Einstein's equations using the assumption that the universe is spatially homogeneous and isotropic. That is the cosmological principle I explained. And the equations govern the expansion of space in homogeneous and isotropic model of universe within the context of general relativity. So to explain the meaning, let's assume that we compress I sort of explained this already, but I'm going to repeat it again because it's important. So let's assume that we compress our 3D universe into 2D universe. In other words, we put our universe in a thin membrane. In this thin membrane, there are several dots that represent galaxies. Now we warp around the membrane and make it a balloon. The membrane of the balloon is our universe itself, including space-time and matter. As the balloon inflated, the dots moving farther away from the home dot and each other. These results show that the farther away the dot is from the home dot, the faster it moves, is moving. So you can explain the same observation that the galaxies are moving away from us due to the expansion of the fabric of space itself rather than the literal movement of galaxies. So, okay, so that is the current understanding of the space-time. That starts from Friedman's equation. Okay, assuming that space-time itself moves. However, if you take this measurement literally, okay, it's not the space itself moves. Actually, all these galaxies are literally moving away from us. Which one is right? Actually, we don't know. We just assume. So that's what I'm going to get to you, okay? With more evidence and with more proofs. That's what I'm going to do today, okay? Okay, so there is an interesting finding here. Very interesting research performed by Professor William Tift at the University of Arizona. Of course, he's retired now. In the early 1970s, he did this work, and he gave us a different perspective here. The Tift showed how often various spacings occur in the Z parameter from galaxies. He stated that there's now very firm evidence that the redshifts of galaxies are quantized. Tift noticed a surprisingly strong peaks corresponding to a certain interval. Redshifts that we are observing are the results of expanding universe, expanding space-time. Then you shouldn't see this discontinuity. You should see continuous sort of distribution of this redshift. But what actually he observed here is this strong peaks. This means that galaxies tend to cluster around preferred values with equal spacings between them. That's really odd, okay? And that has a very strong implication that I'm gonna get to. So Tiff noticed a different pattern of clustering with a different interval as well, and further observations and publications continue to support this phenomenon. And what does this result means? The figure on the right shows a computer simulation result of distant groups, first seen from the exact center. So you see this, so-called here, and you put ourselves at the center, our galaxy at the center, and you perform this mathematical modeling, and the result is here on the left, in a way, on the center here, right? The distance versus number of galaxies. You see this grouping. So this is done by Dr. Humphrey here. Notice that there is difficult to distinguish, however, the groups from the statistical fluctuations from a viewpoint 2 million or whatever light years away. So if you are not at the center, we are away from center, then basically on the right, the graph, basically there is no grouping here. This means that to observe distinct groups of redshifts, we must be near the center of the spherical shell pattern of galaxies shown in the figure on the left. So that is Dr. Humphrey's sort of calculation and interpretation. This implies that we may be cosmologically at the center of the universe or galactocentric universe. And 1997, another independent study of 250 galaxy redshifts by Napier-Guthrie confirmed this, the TIPS observations, confirming that the periodicity of 30.75 kilometer per second observed in the different differential redshifts of 97 bright spiral galaxies scattered around. And in their paper, they stated that the redshift distribution has been strongly quantized in the galactocentric frame of reference. Actually, they said exactly the same thing as Humphrey here. So by galactocentric frame of reference, they mean a frame at rest with respect to the center of our galaxy. Wow, this is a crazy idea, isn't it? But why not? Why not? Actually, we are all brainwashed with the Big Bang idea. Space is expanding. Right? We all have learned that from our birth, basically. Okay, but there are other evidences here. Okay, so the technical literature of astronomy, of course, therefore, completely ignores a galactocentric cosmos. And if I go out to the street or go out to the field and, hey, we are at the galactocentrically, whatever, I'm going to be expired. I'm going to be maybe sent to a hospital. So why? Okay, so that is something that we need to discuss today. Okay, anyway, the technical literature of astronomy almost completely ignores a galactocentric cosmos as a possible explanation. Instead, most astronomers appear to prefer some as yet unexplained microscopic phenomenon. So as yet unexplained is not explained, but there has to be something that affects the light itself, okay, either in its emission from atoms or its transmission through space and so on and so forth. And this is very understandable in a way if you consider the cosmological principle, which says universe is homogeneous and isotropic, and Alexander Friedman used that cosmological principle to solve the Einstein's equation, that is Friedman's two equations. There are two equations, and based which our modern cosmology has been built. Okay,